So we've taken essentially a concept that we've learned earlier, iterative least squares, and we've just wrapped it around a sort of a new formulation. But now let's see what happens when we add in this nonlinearity. And we've sort of seen this before with logistic regression, but let's see what happens with this iterative technique. So let me remind you what this is. We've got our weights W that we want to learn. We have our inputs 1 through x sub n. We're going to do a pointwise multiplication, sum them up, take that output, shove it through a sigmoidal nonlinearity, cap between 0 and 1. That's the sigmoid right there. And what I'm going to do is we established a quadratic error function. And remember, when we established that quadratic error function, it was for an arbitrary f. We didn't actually say what the f was, and now we're going to instantiate these different f's. And what we're going to do is an iterative least squares, or a gradient descent, where we update the value of w. We start at some random location, and we update the value on each iteration. There's my step size alpha according to the label of the training data minus f of the model applied to the training data times the ith component corresponding to the ith weight times the derivative of the nonlinearity applied to the output of the model. So what we saw when f was linear is this simplified quite a bit. The derivative went away, and this was just x transpose w. All right, what happens when the nonlinearity is a sigmoid 1 over 1 plus e to the minus y? Well, the first thing we want to ask ourselves is, what is the derivative? Well, let's do this one first. This is the easy one. If we got x transpose w, well, then we just put that into the exponent in the denominator. So that's relatively easy. What's the derivative of 1 over 1 plus e to the minus y? I'm not going to go through how to do the derivative here, but this is the derivative. It's e to the minus y over 1 plus that quantity squared. And now I've replaced y with x transpose w. Good. So now this is starting to look a little more complicated, but it's actually not that bad. I take x transpose w and I shove it into the sigmoid. I take x transpose w and I shove it into this sigmoid and into the derivative of this sigmoid. And now I have a new update rule. And I can certainly evaluate this everywhere. I know what z is. I know what x transpose w is. I've got a closed form solution for the derivative. And now I can play the same game. Okay, we've got our data. We've got our labels right here, and here's my new update rule. I won't go through this, but if you want to, you can look through this, and you will see that it's exactly the update rule from before. I'm taking the jth weight on each iteration, and I'm updating it by this update rule by adding this, which is the evaluation of the derivative of the gradient in order to get down into that minimum. And that's that. The sigmoid is actually pretty easy. And notice, by the way, that this is an iterative version of logistic regression. With logistic regression, we formulated the problem a little bit differently to get to it. And again, we're doing this here, and it's not immediately obvious, but eventually we're going to start building these things, these neurons up into more complicated networks. And we just have to foreshadow a little bit and say, let's try to do this efficiently, because eventually we know we're not going to be able to build these big, huge linear systems. Now, at this point, it's not at all clear why you want a nonlinearity. It's not at all clear why we should do these iterative techniques over the closed form except for the computational efficiency. It's not clear at all why bundling up these neurons together is going to give us any power, but we're going to see that as we keep going through and looking to see how we get away from these single neurons and the simple calculations that they can do, similar to what we've done in the past, and what happens when we start to combine them in interesting and eventually more powerful ways.